Hello everyone. In this demo, our focus will be on the deployment of deep neural networks on embedded devices. In particular, our focus will be on the so-called pruning strategies, whose aim is to reduce their complexity. We are the ATOS team at University of Torino. Our research focus is mainly devoted to image processing, computer vision and virtual reality. Deep neural networks can solve extremely challenging tasks thanks to complex stacks layers with thousands of neurons. Despite they are just a subcategory of artificial intelligence and machine learning, they are one of the most advanced and powerful tools available to solve complex tasks. There are, indeed, state-of-the-art algorithms for solving a number of tasks, ranging from the most common image classification to image generation, segmentation, object detection, natural language processing applications, AI-based engines to accomplish complex tasks like playing video games, and beyond. Thanks to the ever-increasing computational capability of modern computational infrastructures, it is today possible to train, and for instance, to optimize, extremely complex models, having billions or even trillions of parameters. However, such a complexity, which is not a problem for the most modern computational infrastructures, poses issues for edge computing applications. In particular, the practical use of this technology entirely at the edge, in real-time applications, is currently a challenge. There are several approaches attempting to reduce the size and the complexity of deep models, ranging from the design of custom deep architectures meant for being efficient, to the use of quantization strategies to avoid slow floating point operations, to knowledge distillation. We will focus in this demo on the so-called pruning strategies, where the parameters, not considered relevant for the learn task, are removed from the deep model. Reducing the number of parameters from a model, however, is not necessarily bringing advantages to the overall efficiency of the model. Parameters in deep models are stored in tensors, and the propagation of the signal through these typically happens by matrix multiplication operations. On the left you can observe a typical representation of unstructured sparsity in a deep model's layer. Every row of the matrix represents a neuron, while in the columns we have the inputs of the layer. Each pixel is a parameter, black pixels are removed parameters. In this example, we have 60% of parameters removed. Of course, compressing the unstructured sparsity brings to some representation overhead. However, if we have the same sparsity, but in a structured way, meaning that entire rows, which are neurons, are removed, for the UN compressed model, we have a much lower memory occupation. The same applies also to convolutional layers. We have designed an algorithm to achieve structured sparsity in deep models. In particular, it senses how much the output of a neuron affects the response of the model. All the neurons, whose contribution is not relevant to the result, are removed from the deep model. We call this algorithm SERENE, also known as sensitivity-based regularization on neurons, and it is a pruning algorithm for structured sparsity. We will compare it to Lobster, a state-of-the-art pruning algorithm achieving unstructured sparsity. In order to measure on the field the effect of pruning in the final deployment of the deep models on edge devices, we have customized an Android demo app to measure the inference time in real-time image classification scenarios. We give you the chance to try the app live. You can download the APK using the QR code displayed. This app runs entirely on the smartphone and measures live performance of the chosen deep architecture. From the app you first have the possibility of choosing a destination folder where saving the deep models you wish to download and try. Then, you can download one of the shared models. There are many possibilities. You can choose between baseline models, unstructured prune models and structured prune ones. Once the download is finished, you are ready to go and you can try running the image classification on your device, directly from the device's camera. The top 3 classes are displayed on the bottom, as well as on normalized confidence scores. In the mid of the screen we have measures of average frame per second and the current inference time in milliseconds. We have run some inference simulations using a Huawei P20 smartphone, observing significant improvements in terms of both inference time, and for instance, FPS, and memory footprint, when using the models with structured sparsity. This result puts emphasis on the need for improving algorithms targeting structured sparsity over those greedily removing parameters from the deep model.